So I'm Rupert Young. My interest is in robotics and AI, using PCT for that. So I'm going to talk about applying the evolution of PCT control systems to real-world applications. Mainly, I'm going to be talking about some stuff I've been doing on wind turbines, but also about the ARC competition, or ARC prize, which I find could be a very useful environment for PCT. So just as a recap, so I've developed a process for evolving perceptual control systems because trying to create them manually and tune them manually is very laborious. So I've got this process to do them automatically. So the way it works is you start off with a population of control systems randomly generated with different sizes and different weights. And you evaluate each of those according to some sort of fitness function, which defines how well it controls in its environment. Then you take the best ones that come out of that and you sort of mate them together or merge them together to produce new control systems. And you also do a sort of mutation on them by randomly changing the weights or maybe the sizes of the control systems. And those last three steps are sort of repeated, and with each generation, you sort of improve the success of the control system. So here's some examples that I've applied to sort of simulated control systems. So on the left, you're going to see the inverted pendulum. On the right, the mountain car. I'll come back to the robots in a minute. So with the mountain car, you see that it starts off, it doesn't get to the top of the mountain, but then it starts going back and forward, maybe on the third generation. And if you see on the inverted pendulum was successful very quickly. So the mountain car, it starts making big movements back and forward over each generation. Then it just does a movement just to the left. Then with the subsequent generations, it decreases the movement that is required to the left to get to the top of the mountain. And towards the end, the 10th generation, it just makes a small movement to the left to get to the top of the mountain. So it's sort of optimized the movements or the actions that are required to get there. So the robots at the bottom, this is the result of an evolution process of getting a robot to walk. And this is just showing sort of four examples of walking that have come out of the evolution process. Not particularly elegant, maybe, but it's quite a simple fitness function. It's just how far the robot could move over an episode. But it's using sort of 6 degrees of freedom, so 3 joints in each leg. Okay, so simulated environments are okay, they're interesting, but what I really want to do is apply them to sort of real-world applications that would have some use in the real world. And the sorts of things I've been looking at are sort of energy management systems, plasma control for nuclear fusion, wind turbines, which I'm going to talk about. And then I'm also going to talk about the ARC prize, which is a competition to solve artificial general intelligence. But I think it's a good environment, I think, for exploring multi-level PCT systems. So for the wind turbine, with all these applications, I'm looking for papers that have an environment that is used for reinforcement learning. They tend to be suitable for evolving PCT systems. So this one that I came across, it was using reinforcement learning to control wind turbines. And although it's a simulation, it's actually a simulation of real data. So it's using real data from wind turbines. And basically, so if you're able to get the wind turbine turning into the wind, then you maximize the sort of energy gain. And this paper claimed an energy gain of 0.3% on traditional controllers which might not sound much, but it works out about €2,000 per year per wind turbine, so that's quite a lot. So this paper, it split the data into sort of two different data sets, which they trained and tested separately. One was a sort of steady wind condition, one of a more variable wind condition. And the blue line you see there is the actual real data of the wind direction associated with a turbine. So the orange line is the result of the reinforcement learning algorithm compared with the other lines, which are sort of more traditional controllers. And I think they split into two different data sets. I'm not quite sure why, but I think it's probably because maybe they couldn't get it to work on the general data. But with this, I found that it was just not reproducible. In the paper they linked to code which they claimed to have used, but I tried to reproduce their results with their code, and it just didn't work. And eventually I actually spoke to the first author of the paper on a video chat, and he claimed he agreed that code didn't work, and he claimed that the code that did work was no longer available, which is a bit odd. Anyway, so I applied the process for evolving a perceptual control system to the same data, which you can see on the graphs on the left. And you can see it works pretty well. The control system, the PC control system, follows the wind direction. So this is the equivalent of turning the wind turbine into the wind. And the results I got were better than the reinforcement learning, which you can see on the right there in the red. So for the steady condition, I got 0.35% energy gain rather than 0.31, and for the variable condition, 0.57 rather than 0.33. Something that the reinforcement learning paper did not do was to apply their controllers to the different data sets. So apply the steady controller to the variable data set. So, but I did it with the PCT controllers, and it worked pretty well. So the graphs on the left there show the controller applied to its own data set, but also to the other data set in red. And both show a positive energy gain compared to the traditional controllers. And so the results from the red blocks are shown in the graphs on the right. So this is the controller applied to the other data set, so that it still works. So it's very sort of generalizable. I tried to repeat this with the reinforcement learning, but it was just too unreliable, and I couldn't produce any results that made any sense. So just to conclude this bit, I found that the reinforcement learning was quite unreliable, couldn't reproduce it, and it produced a large network of more than sort of 7,000 nodes. Whereas the PCT system, which is the network on the left there, that consists of 8 control units. So it's a much lower footprint than reinforcement learning, and it's more efficient control and more reliable and reproducible. So I was quite pleased with those results. Anyway, so on to the ARC prize. And ARC stands for Abstraction and Reasoning Corpus. And this is a platform for testing out algorithms for artificial general intelligence. And it consists of a set of visual logic puzzles, 400, which are available for training, and 100 in the test set, which you never actually get to see. So the difference between AI and AGI is seen as, or AGI is like sort of human intelligence, and it's where you only need a few examples to be able to learn a pattern, which is what humans are able to do. But generative AI requires sort of enormous amounts of data to learn any patterns. So generative AI is very bad at solving these visual logic puzzles, which humans are very good at. If you're interested in the money, there's a big prize money involved in this prize. It's an annual prize, and the biggest prize is $500,000, and that's if you get over 85% on the test set. And I think the competition this year finished last week, actually, and I think the last time I looked, the success was about 54%, so there's still some way to go. But I think this would be a good test bed for exploring PCT systems at different levels. So I'll just show you some examples of the sort of puzzles that are involved. So you're given, in this situation, you're given 3 training examples. So you have an input grid and an output grid, and you've got to work out what the pattern is in each of them, or what's required to transform the input into the output. And here, it's fairly easy for us to work this out. And you can see that the a square block of cells turns light blue, and a line of cells turns red. And so for the training, you're given those examples, and then for the test, you're given this test input, and you have to work out what the output's going to be. Here's another example, and as we can see here, so a red pixel is transformed to a red pixel with yellow at the corners and a blue to blue with some orange cells at the sides. But then we can see that also light blue cells don't change, and also pink cells don't change. And you can see that all those patterns are reflected in the example of the test transformation. One other example, here it's quite easy for us to work out that any area that is completely enclosed by other cells turns yellow in the transformation. But these are very difficult for computers to work out. So there's lots of complexities involved in these puzzles. But as a proof of concept, I tried the evolution process on just a simple example. And this is where the grid has, the 2 grids have just different colors. And the colors are represented by numbers. So in this case, the difference between the input and output grid is just a number 3, a difference of 3 at every cell. So in this situation, I think basically the problem is to learn the relationship between the 2 grids. So this is a quick video just showing a set of 3 examples of this being solved by a PCT system, control system that was evolved. So the 2 grids on the left are the input and the output, and the grid on the right is the environment which you're able to modify. And it starts off as the same environment, same as the input, and you need to transform it into the output. So you're modifying the environment to match the output. So in this first case, the grid on the right should turn pink. In this case, the one on the right should turn brown. And then one more. And there's the fitness function, which you see on the right, is a measure of the match between the two grids. There we go. So in each case, it successfully turned the input into the output. So it controlled the transformation of the relationship between the two. So this is just a simplified version of the sort of controller that was evolved. In this case, we're only sort of talking about one cell in a grid. And the inputs down the bottom, the grey ones, are from the input grid, and then the environment. And the environment is the one that you sort of modify. And the values that you see here were not chosen by myself, but they came out of the evolution process. So you can see that the weights on the left-hand side, it came up with a -1 and a 1. So basically the perception there is the difference between the input grid and the environment. It also came up with the reference value, which is correctly to be 3. So this controller, it will change its output or change the environment cell until the difference at the perception function is 3. So this evolution process has come up, and it successfully captured and controls the relationship between the two grids. However, the art environments are much more complicated than that, and it requires a lot of complex prior knowledge and skills, such as geometry, objects, rotations, flips, and counts of the cells there. So I think one way people are trying to tackle this is to use what they're calling a domain-specific language. So this is a set of pre-programmed functions that picks out or extracts these objects and lines, etc., from the grids, and then they're applying a more sort of traditional search approach, which I don't really think is going to get you to artificial general intelligence, even if that's a valid way of looking at it. And it may be possible to use this DSL with PCT systems as sort of pre-processed inputs to the evolution process. But it seems to me that all these elements, objects, lines, etc., they should correspond to PCT levels, intensities, transitions, relationships, etc. So it may be possible to evolve PCT systems for these lower levels, and then combine them into systems with higher levels to provide an overall solution. But I think even if you're not so interested in the competition, particularly, I think this could be a good platform for multi-level PCT research. So, studying what sort of PCT controllers would look like to be the equivalent to all these sort of elements and skills that are required for these tasks. Okay, so there are brief summary. Talked a bit about the wind turbine work that I've done. PCT shows an improvement over the reinforcement learning, and I've talked about the ARC environment, which I think could be a good testing platform for multi-level PCT systems. And that's it. Thank you very much.
Rupert, I've had an impression over the years that implemented simulations like, I suppose The Little Man, and I haven't studied in detail how they're structured, but I've had the impression that the successive levels of control connections don't necessarily align well with the subjectively, phenomenologically identified levels of perceptions as experienced. And I know that Bill talked on some occasions about the possibility of levels within levels, perhaps as a way of reconciling those two things. But I'm not quite convinced that that it's necessary to assume the humanly subjectively perceived or phenomenologically determined levels as governing here. And your genetic process of creating control systems may disclose different kinds of levels or different combinations of levels. Just a possibility I wanted to open up, just to open the creativity there and not be restrictive.
Yeah, really quick, that, especially if it's task focused, I can imagine that might be the case.
Sorry, I didn't hear that. Sorry.
Well, answer that, Rupert.
I would agree that there are probably, or the levels as defined don't sort of match to the more dynamic and messy real world, and I think there probably will be levels within levels, as you say. I mean, I don't, in these systems are evolving, I'm not specifying what type of levels that they are. So it's just whatever emerges from the process. And certainly with the mountain car solution that evolved, you know, before I did the evolution process, I had some sort of ideas of what I thought a solution might be, but it came up with something which I had not thought of at all. So I think this process is going to come up with things that we just didn't think of or didn't imagine. You know, different sorts of arrangements or architectures of the control systems.
So Rupert, they evolve their own input functions. Is that right?
Yeah. So I just take the inputs that are given by the particular environment in question. And yeah, so well, the perceptual functions are basically weighted sums. So it evolves whatever values values are required for that particular environment. So yeah. So yes, perceptual functions are, I don't define those.